Hi, good morning, good afternoon, good evening. My name is Sanjeev Heda, and it is my pleasure today to have the opportunity to present to you on this topic, enabling real-time stability monitoring using SAS Viya and event stream processing. A little bit about myself. I am a senior industry consultant at SAS in our Internet of Things division. My primary responsibilities include providing thought leadership to drive advanced analytic solutions and to help customers uncover value with a specialized focus on industrial and transportation segments. Prior to joining SAS, I was with GE Power for over 12 years, where 9 of those years was in the data and analytics team, with the primary responsibility of enabling condition monitoring using analytics. So for this discussion, to showcase how we can enable real-time stability monitoring, we are using the aircraft engine degradation problem. This problem comes from NASA's Prognostic Center of Excellence at Ames Research Center. The aircraft engine degradation data is generated using simulations from a program called CMAPS. So within this problem, there are a total of 4 data sets, where each data set includes 100 simulated aircraft engines, 1 or more operation modes, 1 or more failure modes. And each data set contains the following information. It contains the unit number and time in cycles. It includes 3 operational parameters and 26 sensor measurements. For this particular paper and presentation, we are using engine number 24 from the FD003 dataset. So what does that mean? This dataset has 1 operation mode, and it has 2 failure modes present, high pressure compressor and fan degradation. And the motivation to select this data is built upon a previously published SAS paper to show how you can create a stability monitoring model. However, that paper did not go further to discuss how you can deploy and operationalize that model using SAS Viya and SAS event stream processing. So this is the motivation and what we'll accomplish with this presentation today. So our end goal, our final output, will be an actionable dashboard that indicates degradation has occurred and warrants further actions. In this case, what we're seeing here is using the open source tool Grafana to show a dashboard that includes the following. We see engine parameters and associated analytic time series outputs. We can see the escalated alerts in the table on the right-hand side, as well as being annotated on the time series charts. When we look at this from an end user perspective, we want to know the following pieces of information. We want to know for our stability monitoring model, what was the target variable behaving and how does that compare with our predicted values with their confidence limits. We also want to look at other engine parameter data so that we can start to diagnose and understand what could be causing the issue. So let's talk about the need for real-time predictive maintenance. So in this example of an aircraft engine, a failure mode does not typically happen instantaneously. The asset condition will degrade over time, where there can be various precursors to indicate that degradation has occurred. The rate of degradation can change depending on the failure mode, the operating of the asset, environmental factors, and resolving the issue can increase in cost over time as damage gets propagated and becomes harder to remediate. So the question becomes, should I always take an action on the earliest indication? And it really depends on 2 items. The first is, what is the cost to remediate the issue? When we think about how do we remove the degradation, we either have to use hardware, we have to mobilize personnel, the asset may be down. We have to think about if there's penalties associated with this because the asset is not able to do what it's being said to do. On the other side, we want to balance this with what is the cost of not doing anything, where if the asset's been degraded, we might see reduced performance, lower output and yield, and it may have a negative image impact to your organization. And so what real time allows you to do is increase your window of opportunity to help make these decisions quicker and to maximize the overall asset performance. So one use case we have is with Volvo and Mack trucks using SAS to enable predictive maintenance. So their challenges include how can they enhance their remote diagnostics and monitoring capabilities of critical assets such as engines and transmissions? How can they minimize unplanned downtime and improve overall vehicle efficiency and uptime? So using SAS analytics, Volvo is able to achieve the following. They're able to apply these analytics to over 250,000 trucks. They're able to achieve a reduction in diagnostic time by 70% and a reduction in repair time by 25%. And they continuously are able to leverage thousands of sensors, creating new analytics to continually improve their capability in providing predictive maintenance for their customers. So now we'll talk about the approach of how we enable real-time stability monitoring. So here's an overview of what was implemented to enable real-time stability monitoring. More details will come in particular areas in the following slides. Starting with data at rest, we have historical data of the aircraft engines with known issues. The first thing we want to do is load that data into our tool. In this particular case, we're using SAS Viya with SAS Viya and SAS Visual Data Mining and Machine Learning. Once that data is loaded, we want to process that data to make it ready to be trained using machine learning models, and then we train our models. In this particular case, we're using stability monitoring to predict potential degradation of our aircraft engine. Other methods can be used, such as neural networks, gradient boosting, to achieve the same objective. So once that model has been trained and ready to be deployed, we can then generate the ASTOR file of the model and register that model into SAS Model Manager. And this is a key step for a couple of reasons. One is that now we have governance behind that model. We know how it was created, what was the audit trail, the version history, etc. And we also know the lineage so that when we want to deploy this model in downstream processes, we know which processes are consuming that model. So in this particular case, we're ingesting this model using SAS event stream processing. So we're using SAS event stream processing for a couple of reasons. One is that it provides minimal latency and action and alerts that can be generated for actions to be taken. So when we talk about real-time alerts and that window of opportunity, event stream processing helps in that regards. And the second reason is when we think about aircraft engines and the amount of data they may produce, that may be a tremendous amount of information to try to take and collect onto a centralized location to be able to process this. So in the case of event stream processing, we're able to push this model to the edge onto the aircraft engine itself. So we have the model linked into Model Manager, which provides lineage. So if there's any changes to this model, we'll get notifications within our event stream processing project. And on the other side, we have the streaming data of the aircraft engine coming in. So then we take that data, prepare it to be scored, and then we score the data in stream using the model we have trained at rest. But we don't stop there because we have a model that says whether we think we're out of the control limits or not. But it really depends on what is the right decision to make and when. And so now we get into the post-processing of the analytic of the results to be able to understand which alerts should be potentially escalated. So the event stream processing analytic is producing these analytic outputs, and these outputs get pushed into an external data system. In this particular case, we have a time series database and an alert database. And then these outputs are visualized and consumed through an operational dashboard. So this is an important feature because no value is realized until an output of an analytic is consumed and decisions are being made. So how do we generate the stability monitoring model? First, we have historical data for the given aircraft engine, and we want to select data to be used for the training and the holdout. And in this particular case, the target variable that we're using is the ratio of fuel flow to a static pressure, as research indicates this is the best indication of degradation for the aircraft engine. Next, we create multiple models to compete to see what does the best job in predicting the behavior. In this particular case, we are using a mean, a regression, and a ARIMA model to see which one is the best predictor. Input variables into these models can include pressure at the fan inlet, total pressure at the bypass duct, or corrected core speed. So once we have the models and they've been created, we use the holdout period to determine what model method performs the best in predicting the target variable. In this particular case, we're using MAPI, the mean absolute percentage error, to determine how well does that model perform during the holdout period. In this particular case, the REMA model is selected as the best one and is close to the regression model created. So the best model is selected and becomes the champion model. So once the champion model is selected, it can be registered into SAS Model Manager and be consumed into SAS Event Stream Processing. This overall process was done using Jupyter Notebook that interacts with SAS via using the Python package SWAT, which stands for Scripting Wrapper for Analytics Transfer. The Python package SWAT allows users to execute SAS actions and process all the results using Python. Great. So now we have our model. And now the question is, how do we get that model to score in real time? So here we have a simple flow to show that process with 3 key steps. First is the model manager, where we have our stability monitor model registered, which provides the governance and lineage, and that model can be used in multiple places downstream, including SAS Event Stream Processing. Then within SAS Event Stream Processing, we can include the model for scoring. We can pre and post process data that is coming into the analytic to help make actionable alerts. And we do this through a graphical user interface called Event Stream Processing Studio to create said analytics. Once this analytic is created and been validated, we can publish and version this analytic and deploy this analytic to wherever it needs to be and monitor its status using SAS Event Stream Manager. And really, this is a continuous process because over time, the requirements in the model will change where we need to continuously interrogate to make sure that the model is performing as expected. And so what we see here as the graphic change is this is the SAS Event Stream Processing Analytic within ESP Studio. And what we see here is that the scoring of the model is just one window. The results are analyzed to determine what decisions are needed and when. What about the analytic outputs? So value is not realized until an action is taken that otherwise would not have been taken. Analytic outputs really depends on the business requirements and process. As you have multiple users and individuals that consume this information, that information could be maintenance workflows, time series databases, alarm management. And really, it comes down to the analytic outputs should align to the organization tools and interfaces. We don't want folks to have to use 1,000 tools for someone to fulfill their job, and we really want this to be as frictionless as possible. SAS and SAS Event Stream Processing provides flexibility to integrate with existing systems and platforms. To highlight this, for this particular presentation, we are using open source components. For the external data system, we're using a Postgres database, and for the operational dashboard, we're using Grafana. And with that, we will now go into our demo. For this demo, I want to cover 3 key items that are important to accomplish in this deployment and operationalizing these stability monitoring models. The first is how we create that stability monitoring model, and in this particular case, we use a Jupyter Notebook in conjunction with the Python SWAT package to be able to interact with the SAS Viya and CAS system. So we see we make the connection to the CAS system. We are able to load action sets. In this particular case, the data that we're using for training is on my local PC, so we load it into pandas, and then we can manipulate that data, modify it as needed. That data eventually gets uploaded as a CAS table. And so then we start preparing this training data as we typically do, determining which time series of data we want, what's our target variable, until we get to the core options that are used or selected for creating the stability monitoring models. So in this case, we can select the inputs, the types of models. In this case, we're doing a means, we're doing a regression, we're doing an ARIMA model, to where we submit this into CAS, we get the score outputs, and it's nice because those results get returned back into the Jupyter notebook where we can take that same data and plot it using standard packages like matplotlib to make a determination of which model performed the best in predicting the target variable. In this particular case, we see that the RIMA model is the one that performs best with a project ID of 1 with a model ID of 2, and that we are able to score additional data just to get confirmation of how it performs. And then finally, because we have an A store created, we can take that model and then register it within Model Manager so that we can consume it downstream in other processes. So in this case, we have the model name as S model SWAT and then the project name as Stability Monitoring. And a key piece here is that the A store actually contains all three models, and so we need to make sure that when we score it, the SAS code that's used to score the A store model knows which model we want to select. And that's getting into step number 2. We go into Model Manager where we can see our new model that we've created, new project called Stability Monitoring here, and we see our model that was created. We do want to create this as a champion, but as I mentioned before, we need to make sure that when we score this model that we are using the ARIMA model because that was determined to be the champion. To make that change, all we have to do is click into this model information. We can see the associated files with this model, and we want to look at the score code, the determine that loads and be able to invoke this model for scoring. And so in this particular case, we added 2 lines right here where we set the project ID and model ID for the A store to know which one we want to score against. And so as we saw, the champion model was project ID 1 and model ID was 2. We added this here so that when we score the model, we are using the ARIMA model that we expected. We would save this and then go back into the project folder and then make sure that we have selected this as the champion. The reason why champion selection is important so that one, downstream processes know which model would be the best one to choose. In the case of event stream processing, the model has to be a champion, otherwise it can't be selected. So then we get into step number 3. We have our model registered, it's ready to be consumed. How do we get that into SAS event stream processing? And so what we're seeing here is the completed project that shows from ingesting data to analytic outputs and alerts of completing the full process end to end. And so in this particular case, we're reading a CSV file of the historical data to replay and information, and then we're going to score that data with our stability monitoring model. And so to ingest that model, we have a calculate window where we're saying the calculation is user specified, and when we say how is that handler defined, we can then select the import a module from SAS Model Manager. And so we see the same repository as we saw in SAS Viya. So we can look to see our stability monitoring model project. We can look to drill down further, and then we can see our champion model that we have created listed here, where we can look at its various inputs and outputs and other pieces of information. So I've already incorporated this in, and as I mentioned before, this is just one piece of the puzzle. Downstream of that, we then want to post-process those results to determine when is an actionable alert required. So in this case, now we're ready to execute. So we'll enter into test mode. Once this is completed, we would then publish and version this analytic and then deploy it onto servers using Event Stream Manager. For this particular case, we're just running a simple simulation to execute that data. As I mentioned, running the CSV data, we can start to see the data streaming in. Outputs of this is that the data is really going into Postgres database, both the time series and the alerts. And what we're seeing is the same dashboard that we saw in the PowerPoint, where we had the various time series data being presented, both the inputs and the analytic outputs. We can see alerts being generated, and we can see those being generated both in a table as well as annotated alerts being shown on these graphs so that we know when those abnormalities are occurring. Thank you for your time today to learn how you can enable real-time stability monitoring using SAS Viya and event stream processing. If you have any questions, please feel free to reach out to me at sanjeev.heda@sas.com. Note the materials that we use to create these stability monitoring models to be able to incorporate these within a SAS event stream processing are included in the GitHub repository for this conference. Thank you and have a good day.